Hello, everybody. Let's go ahead and continue from where we left off on Thursday last week. So, the last thing we talked about was ionic bonding. And in ionic bonding, we talked about how ionic bonding is when electrons get transferred. And I like to call it stealing. And, uh, and so remember that elements that are on the right hand side, they're usually the nonmetals. And those nonmetals like to steal electrons from the metals to complete their octets, right? To get 8 electrons in the outer shell. And all that is so that they can actually attain a electron configuration, which we call isoelectronic, right? Meaning the same number of electrons in the valence shell or the outer shell as a noble gas, right? So that's where we left off on Thursday last week. So that takes us into talking about covalent bonding, right? So where ionic bonding is about the transfer of electrons or metals giving up electrons to nonmetals to form an ionic bond, covalent bonding is about two atoms sharing electrons, sharing a pair of electrons in order to achieve the octet, right? So if you take a look at the slide I have up right now, let me get a pencil going on here, right? Um, we're looking at actually two hydrogen atoms right now, right? These are two hydrogen atoms. And the plot that you see towards the right here is called a van der Waals plot. And what the van der Waals plot does is that it gives you it shows you the interaction between the two atoms of hydrogen as they get closer and closer together. And when you when you look at the hydrogen atoms and they're so far away from each other, there's like no interaction between those atoms at all. And so here you have two hydrogen atoms. They're kind of far from each other, right? And so they don't even see each other. They don't interact with each other at all. But as the hydrogen atoms start to become closer to each other, right? One of them sees the other one, and they're like, "Man, I want to be with that hydrogen atom. Maybe we can share electrons." And so they get closer and closer and closer until they reach this distance from each other that's perfect for them just to sit next to each other and share electrons and minimize the kinds of like repulsions that would happen between two atoms. Because remember that the center of an atom is a positively charged nucleus, right? And so for two hydrogen atoms, the perfect distance, right, is 0.074 nanometers, which is a very tiny distance, by the way. But right at that distance, it's the perfect distance for the two hydrogen atoms to be next to each other and interact with each other and not be so close to each other that they just collide with each other. And then there's a crap ton of energy, right? Or be so far away from each other that they don't see each other at all and don't interact at all, right? And so if you recall back in the ionic bonding, remember that both sodium and chlorine, right, were kind of crazy elements, right? Sodium was explosive when you let it hit water, and then chlorine was a poison gas. But when you bring the two together to make an ionic compound like sodium chloride, then sodium chloride is actually a much lower energy molecule, right, or a compound than either sodium and chlorine are separately. And so being together calms them down and brings them down to a low energy. They're just like people, right? It's fun to be all exciting and stuff like that and have a crazy life, but eventually you want to settle down and be low energy, right? Not like low energy, but be stable. So the same thing happens with covalent bonding. In covalent bonding, instead of transferring electrons or stealing electrons from each other to attain that lower energy level that's more stable, two nonmetal atoms will share electrons. And in this case, these two hydrogen atoms share the electrons. They're about 0.074 nanometers apart, and they're perfectly suited right there, perfectly happy right there. And they're at the lowest stable energy. If they're far away from each other, their energy goes up. And if they're too close to each other, their energy goes up. So that is the perfect distance. 0.074 is the perfect distance. So, just to make sure you're actually here and you are listening to the lecture and you're watching the videos, let's try to go ahead and answer this question here. All right. So, what is the distance at which two hydrogen atoms are the most stable? Is the answer A, 25 nanometers, B, 0.074 nanometers, C, 36 millimeters, or D, 74 millimeters. I'll give you a couple of seconds to answer that question. Do, 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 do. Do, 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 do. Do, 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 do. Do, 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 do. All right. So go ahead and answer the question in your by scanning the QR code. That's going to be your attendance. But also feel free to answer the question in the comments if you're watching this on YouTube. And so let's see who gets it right. And if you don't know the answer, you can just go back a slide. It's there. So remember we were talking about Lewis structures when we were talking about ionic bonding. And so just to recall, the Lewis structures will allow you to visualize the valence electrons or the outer shell electrons around the atom. And so just, as a reminder, remember hydrogen has a one valence shell, lithium has one valence shell, sodium has one valence shell, right? Oh, sorry, not valence shell, but one electron in the valence shell, right? Beryllium has two electrons in the valence shell. Magnesium, same thing too, because they're in group two. Group three valence electrons in the outer shell, right, with boron and aluminum. Then we jump onto the other side of the periodic table. 7, right? Valence shells for fluorine and chlorine because they're in group 7, so they need one electron to be happy. They steal that away from. They can either share with another nonmetal, or they'll steal one away from the nonmetal from the metals, right? Group 6 valence electrons, right? So right there, these two are the two electrons that are unpaired, so they both need one electron to be happy, right? So maybe they'll combine with a group 2 element so that they can uh, be uh, be happy with their 8 electrons. But that's with ionic bonding. So what does it look like when two atoms share electrons through covalent bonds? What does the uh, Lewis structure look like, right? Or the Lewis symbol look like, right? So let's look at hydrogen. So when you see hydrogen here, right? Hydrogen has that one electron in its outer shell, and right there. And when they come together to share electrons, that's what it looks like, right? And now hydrogen is bonded to the other hydrogen, making the H2 hydrogen gas molecule, right? The diatomic. And so you can see how we kind of denote or indicate that sharing of electrons happen by having two electrons in between a pair of atoms, right? Most commonly, though, this is what we do. We just change the two electrons into a single straight line, which represents a single bond, right? We'll talk about the other types of bonds in a second, but that's a single bond where there's only two electrons being shared, right? That's the covalent bond. We can do this with also chlorine. Here's hydrogen right there, nonmetal. Chlorine, right, nonmetal. They come together, and now hydrogen and chlorine are sharing those two electrons right there. We change that into a straight line for a single bond, and now we have a molecule called hydrogen chloride, right? Again, the noble gases they tend to not need to have any bonds because the noble gases already have 8 electrons, so there's no reason for them to share electrons or even steal electrons or give up electrons. They have 8. They don't want to, except for helium, they all have 8, so they're just happy the way they are. But you can see the trends though, right? As we go across the periodic table, if the element is in uh, is in group 4, like carbon, then it makes 4 bonds, right? Because it has one lone pair, sorry, not lone pair, one unpaired electron, two unpaired electrons, three unpaired electrons, four unpaired electrons, meaning that it needs to have 4 more electrons to have its outer shell full, and so it will make 4 bonds, right? To do that. So here's carbon right here making 4 bonds, right? And these 4 bonds can be 4 bonds with like anything that can form a single bond. So for example, hydrogen. So we have hydrogen here like that, and like that, right? And we've made the molecule methane. We move into group 5, right? Group 5, remember, if you're in group five, that means you have five valence electrons, and so you need three electrons to be happy. That makes eight. And so these right here are the three unpaired electrons that need to have bonds with other electrons, right, to make this group happy. Anybody in this group happy, namely nitrogen, right? And you see here that means that if you need to have three electrons to be happy, it means you can form three bonds, right? Oxygen needs two electrons to be happy because it's in group six right there. And so it can form two bonds. And then group 7 atoms have 7 electrons in the outer shell, so it just needs one electron sitting right there. It can share with somebody else. So, for example, fluorine, one electron, and so it means it can form one bond. And then, of course, we have neon here, which is a noble gas. Doesn't need to share any electrons because it's already got 8. So, like I was talking before, there's not just single bonding, there's also double and triple bonding too. So the easiest way to use to show you triple bonding is with just with examples, right? So let's look at carbon, for example. So carbon right here, like I said before, has one unpaired electron there, one unpaired electron there, one unpaired electron there, and one unpaired electron there. If we go back to the previous slide, we can see that carbon can actually form 4 bonds, right? And in this example, it formed 4 bonds with hydrogen, right? Because hydrogen can only form 1 bond. But how many bonds can oxygen have, right? Oxygen can have 2 bonds, right? One unpaired there and one unpaired there. This is the same thing over here with this oxygen, right? They both have 2 unpaired electrons. What that means then is that oxygen and carbon can share 2 pairs of electrons each, right? And so when we do that, we can look at oxygen on this side sharing 2 pairs of electrons, right? And then the oxygen on this side sharing 2 pairs of electrons. If you count everything up, say if you count all these guys up right here for the carbon, notice carbon now has 8 electrons, right? And then if you count up all the electrons here for the oxygen, one of them on the right side, now oxygen has 8 electrons too. Do you see how they're sharing electrons to make 8? This oxygen is also sharing electrons to make 8 with this carbon, right? And so if you recall, if you have one pair of electrons being shared, that's called a single bond. But how many pairs of electrons are being shared between these two atoms here? Well, that's one pair shared, 2 pairs shared. That's called a double bond. And so we indicate a double bond with a double line, right, between the two atoms, right? Same thing with this one. We have 2 paired electrons, two pairs of electrons being paired right there, right? And that means it's a double bond, right? So these are called double bonds. Whenever two atoms share 2 pairs of electrons with each other, that's called a double bond, right? And so I did all this circling up here, but there's a better picture right here, right? Where you can see how if you look at carbon by itself with its shared electrons from oxygen, right? It's got 4 on this side, 4 on this side, making it have 8 electrons. So it's happy. If you look at just oxygen atom, right? It's sharing 4 electrons with carbon. It's got 4 of its own, so it's got 8 electrons. It's happy. Same thing here with this oxygen, right? It's got 4 of its own electrons, and it's also sharing 4 with carbon, so it's happy with 8. So it doesn't stop with just double bonds, right? We can also do triple bonds as well, where atoms can share 3 pairs of electrons. So nitrogen does this, right? Remember that nitrogen is also one of those diatomics, so we call it N2, right? Because it's always got its natural form is it's going to be 2 nitrogen atoms together sharing electrons. But how does it do it? Well, nitrogen has 3 unpaired electrons, right? Both of these guys have 3 unpaired electrons. So what does that mean? That means they are primed to share 3 electrons with each other, right? To get to 8. So this one gets shared with this one gets shared with this one, and then this one gets shared with this one. And so now you see that nitrogen is sharing 3 pairs of electrons. When you have three pairs of electrons, we call that a triple bond, and we indicate that with three lines between the atoms that are sharing the electrons, right? And once again, if we just break it down, we can see that if we look at one nitrogen right here, it has its own pair of electrons and it's sharing three pairs with the other electrons, which makes eight electrons. Sorry, three pairs with the other nitrogen, which makes eight electrons. You look at this nitrogen right here, right? It also has one of its own pair, and then it's sharing three pairs of electrons with the other nitrogen, making it have eight electrons, right? So, again, the difference between an ionic compound and a molecular compound or a covalent compound, the difference between a ionic compound and a covalent compound is that in ionic compounds, the metals will lose electrons to nonmetals in a transfer of electrons, or I like to call it stealing, where the metal will steal an electron, sorry, a nonmetal will steal an electron from the metal, right? Uh, and it will actually change its charge and everything, right? Becoming an ion. Uh, Remember cation being positive and anion being negative. But for a covalent bond, right, or a covalent compound, these electrons are being shared. So each of them have equal ownership of the shared electrons, and each of them will have eight electrons from that shared ownership. Okay. So let's compare and contrast a little bit the difference between a ionic compound and an covalent compound, right? Well, unlike ionic compounds, covalent compounds are composed of individual molecules, right? With a specific molecular formula, which is very different from an ionic compound. Remember, we looked at salt, and salt was a cube, right? A crystal cube that had alternating chlorine and or chloride and sodium atoms back and forth, or ions back and forth, right? And they were just kind of alternating sodium chloride, chloride until you had a big crystal of salt. And each one of those sodium chloride pairs, right, is called a formula unit, right? It's a little different with covalent compounds. A covalent compound doesn't do that. It doesn't have the every other atom kind of arrangement in a crystal. A covalent compound is made of a whole bunch of individual molecules, right? Also, covalent compounds are the bonds between covalent compounds, which are covalent bonds, are strong, but the individual molecules, they're only weakly attracted to each other, right? And so a good example of this is that when you sodium chloride, which is an ionic compound, when you throw that into a frying pan, you can't burn it, right? It doesn't melt or anything. And that's because an ionic bond between the individual and chloride and sodium ions is strong, right? And so it takes a lot of heat to break those chloride bonds, sodium chloride bonds, which is actually interesting because you could just dissolve them in water and they'll break apart easily. But as far as melting them or burning them, it just doesn't happen because your the flame that you have on a stove is just not hot enough. But if you were to do the same thing to sugar, which is a covalent compound, which has covalent bonds in it between carbon, hydrogen, and oxygen, even though the individual sugar molecules, right, are very strongly held together, the carbons and the hydrogens and the oxygens, they're very strongly held together. Um, the the individual molecules, uh, they're being held together very weakly, though, right? So the atoms are being held together very they're being held together very strongly, but the molecules themselves, the individual molecules of each sugar, right, is only held very weakly together, right? And so that's why when you put sugar into a frying pan, you can melt the sugar into caramel, and you leave it there long enough. What's going to happen to it? It's going to turn into just black ash, right, or black carbon charcoal, right? And so that's a big difference between ionic compounds and covalent compounds. Um, Compounds formed only with nonmetals are covalent, which you knew that already, right? Just remember that ionic compounds are always going to be a metal and a nonmetal together, get a transfer of electrons, whereas covalent compounds are always going to be two nonmetals together in a sharing of electrons, right? Um, And the rest of this you should already know too. Compounds of metals and nonmetals are generally ionic. And then compounds of metals with polyatomic ions are also ionic. Those are those kind of those metals that weren't happy with just one nonmetal. They had to have more than one nonmetal, right? Like the phosphate ion, PO4, right? Um, and such. Those are the polyatomics. Those are also ionic too. The polyatomic ion itself isn't ionic. That's definitely covalent, but in the end, the polyatomic ion as a whole is a ionic compound. Compounds that are gases, liquids, or low melting point solids are usually covalent, right? So again, sugar is a covalent compound, and so it has a very low melting point. You can put that into a frying pan and it will melt easily. And if you leave it in there for too long, it'll just burn. You can contrast that then with, salt, which will be in a frying pan forever. You'll never burn it because the frying pan doesn't get hot enough. Compounds that are gases, liquids. Oh, I already said that. Sorry. Compounds that conduct electricity are, when melted, are ionic. So ionic compounds not only can conduct electricity while they're dissolved in water, their melted forms can also uh, dissolve conduct electricity. So, some more comparisons between ionic compounds are crystalline solids, kind of like just like I was saying with salt. It's a crystal. It's like a cubular crystal. They have very high melting points and high boiling points. That's the reason why you can't just melt table salt in a frying pan. And again, they will conduct electricity when they are melted, right? And then they're soluble in water, but not in nonpolar liquids. And what that is that you can dissolve salt in water really easily, but you can't dissolve salt very easily in something like ethanol, right? Because both are very polar. And we talked about polarity. We'll talk about polarity in a second, but there's a reason why salt dissolves in water so well and sugar doesn't. Where ionic compounds, at room temperature in our normal environment are solid crystals, covalent compounds are gases, liquids, and solids. They can be anything like that, right? They also have very low melting points and very low boiling points. That's why sugar can melt real easily in a frying pan. They can, and then eventually just kind of break down into carbon dust. They're very difficult. It's very difficult to conduct electricity uh, using nonmetals, right? Metals are the good conductors, so covalent compounds only have nonmetals, so they're not going to conduct electricity very well. And then covalent compounds don't dissolve in water very well, right? But they do dissolve in things like methanol, ethanol very well, like drinking alcohol. And that's because covalent compounds are not as polar. Again, we'll talk about that in a second. So now answer this question in the comments, right? Or also using the QR code. Which of the following is not true about covalent compounds? Is the answer covalent compounds are composed of individual molecules with a specific molecular formula? Is it B, covalent molecules strong bonds? Is there a word missing there? C, individual covalent molecules are strongly attracted to each other, or all the above are true. I'm pretty sure B is supposed to say covalent molecules have strong bonds, right? So, one more time. Which of the following is not true about covalent compounds? Covalent compounds are composed of individual molecules with a specific formula. Covalent molecules have strong bonds. Individual covalent molecules are strongly attracted to each other. Or all of these are true. I'll give you a second to answer those, either in the comments or in your QR code, just to make sure you're actually watching the video. All right, go ahead and answer that. So, what is electronegativity then? Electronegativity is the tendency for a molecule, no, not molecule, sorry, a non-metal atom to attract electrons to itself. And so that kind of is self-explanatory, right? Because about because nonmetals like to steal electrons from metals, right? So that just means then that they like to attract electrons to themselves. So where are the strongest electronegativity atoms, the ones that attract the most electrons? They're in the upper right-hand corner. So if you look in the upper right-hand corner of the periodic table, things, except for the noble gases, things like chlorine and fluorine, right? Look at their electronegativity numbers, right? Fluorine has an electronegativity of 4, right? Chlorine has an electronegativity of 3. Oxygen has an electronegativity of 3.5. So those guys have very high electronegativities. They will just do anything to be with electrons or to get those electrons to fill their outer shell. Compare that to the metals, all their electronegativities are really low. And that's because, like I said, nonmetals are much more likely to steal an electron because they can attract the electrons from the metals, right? So just one more time, as you go across the periodic table from left to right, right, and you go up the periodic table, right, those are where the stronger electronegativities are. As you go downwards, right, and towards the left, then the electronegativity is not as strong. It gets weaker. So I was talking earlier about polarity. What is polarity? Well, polarity is when you have two atoms, right, and they have different electronegativities. You put them together, and then one side has a partially positive side, and the other side is partially negative. That's called a polar molecule. So it's just like a magnet, right? Magnets are polar as well. They have a north pole and a south pole, right? Also known as a dipole because you have two poles, right? Well, molecules can do that too. And molecules that have two electronegativities that are two atoms with electronegativities that are very different from each other, bonded to each other in ionic compounds, they are very polar molecules. So you notice how hydrogen's electronegativity is 2.1 and chlorine's electronegativity is 3.0. So this is interesting. We have a nonpolar molecule here, right? And the reason why this one is nonpolar molecule is because it has beryllium in the center, right? And that's partially positive, very true. But then it has two hydrogens on both sides that are partially negative, okay? Uh, so what makes this thing nonpolar is that it's symmetrical. If you divide it down the middle, right, it's the same charge on both sides. And that's why it's nonpolar, right? Notice how if we divide this thing down the middle right here, it's definitely polar because it's not the same on both sides. It's not symmetrical. So a good general rule is that if the molecule is symmetrical, it's probably nonpolar. So we can actually use this thing called VSEPR theory. VSEPR, VSEPR. That stands for valence shell electron pair repulsion theory. And what that means is that whenever you have two lone pairs of electrons, like this one here and this one here on the oxygen of water, you will push away bonds to minimize the energy of like repelling between the electrons, right? And so when you do that, it makes it where the bond, you would think that the bond angle here between the oxygen, the angle right here, this angle between the two hydrogen bonds, right, of the right there, that angle right there, you'd think that would be 90 degrees, right? But it's not. It's actually not 90 degrees at all. It's actually 109 degrees. 109.5, I believe. Same thing here, right? Again, the electron pair repulsion theory, the valence shell electron pair repulsion theory, right, makes all of these guys, instead of being 90 degrees, 109 degrees. I think it's 109.5, but don't quote me on that. I'm pretty sure it is right, right? If there wasn't, right, if there wasn't this for separate theory where the electrons push each other away from each other, like they push away from each other so that to make it so that they are less energy, right? They minimize the energy of repelling between them. Then all these right here would be like 90-degree angles, right? But if separate does exist, the electrons are pushing away from each other to minimize energy, right, of repelling, because remember electrons are negatively charged, and so they repel each other when they come close to each other. So uh, that's that's how it is in real life. It's not 90 degrees; it's 109 degrees because these electrons are pushing away from each other to minimize energy, and that's called the VSEPR theory or the valence shell electron pair repulsion theory. So this can actually give us some patterns right here for shapes of different molecules. If you have a carbon dioxide, right, with a carbon and two oxygens attached to it. Notice how they're both sharing a pair of electrons, two pairs of electrons, right? When you have two electrons like that, or sorry, two atoms just symmetrical like that, we call that linear, right? This is definitely nonpolar because when you split it down the middle, it's the same on both sides. That's definitely a nonpolar molecule because it's symmetrical. This slipper also causes the trigonoplanar when we have three atoms attached to a single atom in between, right? And so this bond angle right here is actually probably very intuitive if you're good at geometry, but it's a 120-degree angle, right? But notice that when you split it down the middle, right, it's symmetrical on both sides, so it's not polar. Oh man, let's talk about this guy now. Tetrahedral, right? What is tetrahedral? Tetrahedral is basically a four-sided shape, right? Like a three-dimensional polygon. So a four-sided three-dimensional shape that's not a square. Okay, kind of like a diamond, but not a square. Okay, and so all these guys here, like for example, the carbon with the 109-degree angles, 109.5, water here, right? They all are tetrahedral because of the Weissenper theory. And also, it's hard to tell here because it's kind of drawn weird, whoever drew this, but if you were to split it down the middle, it's definitely symmetrical as well, so it's non-polar. So you can also have ones where it's got the three bonds. This is ammonia, which is what's used for cleaning windows, Windex and stuff. Its electrons up here, right? That lone pair of electrons there, because of a separate theory, pushes these bonds downward, making a pyramid, right? And so we call that the trigonal pyramid because it's a pyramid in the shape of a triangle. And if you try to cut it down the middle, you can see how it's not symmetrical at all, right? And so I actually messed up there. I drew the line down the middle the wrong direction. Let me fix that. How do I erase this? Oh yeah, that's right. I gotta go here. Oops, wrong button. There we go. So if you cut it in half right here, right, you can see how it's got the nitrogen with no hydrogens at the top, and then the nitrogen with all these hydrogens at the bottom. So it's definitely not symmetrical, and so it's polar. And then water, even though this tetrahedral here, right, is nonpolar, that's because it's got chlorines all around it. Water is different, even though it's also tetrahedral. It's got lone pairs up here, right, and it's got hydrogens down here. So you cut this down the middle, right? It's very partially negative at the top and very partially positive at the bottom, and so that makes it polar. And I don't know why they call it angular. We actually call it in chemistry. You call this the bent, right? Bent. And so this is just a kind of a close-up view of what water is, right? And so if you look at water, you would think that water was, you know, linear, right? Because it has the two hydrogens on either side and then two lone pairs. But if you look at the molecule three-dimensionally, the two lone pairs of electrons, the ones that don't bond at all, they actually are at the top of the oxygen, and then the bonds are at the bottom of the oxygen. And so these guys push down, you know, and these guys push up, and they just kind of go back and forth with it until they can stabilize into a certain configuration that would make them minimize their molecule, minimize their energy. So if you cut this guy in half right here, then you can see that it's not symmetrical on both sides. It's negative on one side, positive on the other, and so that's why it's polar. How do we know for sure, though, that water is polar compared to other things? Well, here is a stream of water, right there. And what this is that it's a plastic rod that's got some static electricity on it, right? Like we just took like a plastic like a PVC pipe, and we rubbed it with like a cloth to give it some static electricity. And when we did that, um, and we brought it close to the stream of water, since the static electricity is negative, right? Because of electrons, it actually attracts the positive side of the water, right, which is the hydrogens, and makes the water do the slow stream. If you were to do the same thing with this molecule, which is carbon tetrachloride, you saw this earlier. It looks like this. It's a carbon with 4 chlorines attached to it, right? Remember that this guy right here is nonpolar. And since it's nonpolar, it doesn't cause any kind of deflection in the stream. The stream still goes straight down. So you can go through this little flow chart here to figure out whether or not a molecule is polar or nonpolar, right? And whether it's a covalent bond or an antibond, right? So let's say you have 2 atoms. Are the electrons being shared or are they being transferred? Or, let's say stolen, right? So if it's being stolen, that means that you have a metal interacting with a nonmetal, right? Plus a nonmetal. And that means then it's ionic bonding. That means then it's also got a positive ion, which is a positive ion, right? When it loses an electron, known as a cation, and then negative ion, known as an anion. God, that's terrible writing. Let me write that again. And ion. There we go. All right, and so that's ionic bonding. But say the electrons are not being shared, right? They're not being stolen, right? They're actually being shared between the 2 atoms. That means what you have is covalent bonding. That means that you have a nonmetal plus a nonmetal. If there's one thing that you should take away from this class, right, is that ionic bonding is a metal with a nonmetal, whereas covalent bonding is a nonmetal with a nonmetal. So once you've determined that it's covalent bonding, you ask yourself, are the electrons being shared equally? If they're being shared equally, right, then you have a nonpolar covalent bond, right? Right. So again, that's like symmetrical, right? But if they're being shared unequally, and you have a positive on one side and a negative on the other side, we call that a polar covalent bond. They're still covalent bonds, but they're polar. So here's another question for you to answer. Which of the following properties of ionic compounds is not true? Crystalline solids, right, are made of ions. High melting points and boiling points. Ionic compounds have high melting points and high boiling points, right? They do not conduct electricity when melted, or many of them are soluble in water. Which one is the right answer? I'll give you a second to answer. Do 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 do. Do 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 do. All right. If you don't know the answer, go back a couple slides. Right. So we were talking about dissolving earlier, right? The fact that that ionic compounds can dissolve. How does it actually even happen? Well, if you take a close look at a salt crystal, which we have right here, this is a salt crystal, right? Water molecules will come over, right? And the positive side of the water molecule, which is the hydrogens right there, they're attracted to the negative chlorines, which kind of makes sense, right? Because opposites attract. And so what they'll do is they'll pick that chlorine or chloride off of the crystal, right? And surround it so that its positive sides, right, are pointed towards the chlorine, right? Water's really cool because you can also do it the other way too, where its negative side, right? I was trying to draw an arrow there, right? That this side of the water molecule is negative, right? It has the 2 lone pairs of electrons. It's attracted to what? The positive sodium right there, right? Or maybe even this positive sodium right there, right? And so it'll pick it off of the crystal and surround it, the sodium ion, so that its negative side, right? Its negative side is pointed towards the positive ion. And that's how water dissolves things. It will surround itself using either its positive side or its negative side, and it will surround it using both of those sides, right, to separate ionic compounds. That's why ionic compounds dissolve in water so well, because they're always made of, not all of them, but most of them, they all dissolve in water so well because they're made up of an ion, a cation, and an anion. And cation is always positive, and so the negative side of the water, which is the chlorine side, sorry, the negative side of the water, which is the oxygen side of the water, where the lone pairs are, will surround itself around the positive metal, right, or the positive cation. And then vice versa happens with the other side of the water molecule, where the positive side of the 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 water molecule, right, which is the hydrogen side, will surround itself around the negative anion, which is the chloride, right? And so this it can do this with a lot of most ionic compounds, and so water can dissolve tons of different ionic compounds. Not every ionic compound, but most. So when you've completely dissolved salt in water or any ionic compound in water, that means that each ion has been surrounded by water molecules, right? And it's floating around in the water molecules happily. So a second ago, I told you something. I said something called. I said a phrase that was opposites attract, which you already knew that, right? Because to not do it's not just opposites like opposite people attract, like early on in life before they settle down, but molecules are the same way. Opposites attract. Negatives are attracted to positives, right? Positives and positives repel each other, and negatives repel each other, right? So for the most part, in chemistry, opposites attract. But there's one caveat to that, and the caveat to that is that like molecules. What that means is that like likes like, or like molecules will dissolve other like molecules, right? So, for example, water, when you put oil into water, they separate, right? Happens in your vinaigrette salad dressing all the time. They'll separate. And the reason why is because oil is so different, right, from water. It's very nonpolar. If I can spell this right. There we go. It's very nonpolar. And it's nonpolar too because it has all these carbons and hydrogens in it. Remember, and I drew that out before with methane, right? And we split it down the middle, and it's symmetrical, right? And so it's very nonpolar. Water, on the other hand, though, right, is very polar, very, very polar, right? Because you split this guy down the middle right here. We'll do one of them, right? We have a negative side on this side, right? The symbol we use that for that is this, by the way, partially negative. And then over here, it's partially positive. So it's super polar. And since they are not alike, they separate. So the general rule is like dissolves like, or like likes like, right? And so those are they're like the two main rules in chemistry: opposites attract, and like likes like. Okay, so opposites attract when you're talking about putting two atoms together, right? Um, Positive and negative. But then like likes like is when you have two different molecules and you're trying to mix them together, right? And the two molecules, if they're similar to each other, they'll mix together. But if they're not similar to each other, they won't mix together, right? So that's the principle of like likes like. Water also does this thing called hydrogen bonding too. And in hydrogen bonding, right, water molecules will make this like it's almost like a hexagon shape, right? The way it works is that the electronegative atom, which is the oxygen, right, will hydrogen bond with the hydrogen, right? But the hydrogen also has to be connected to another electronegative atom, in this case, another hydrogen, right? And so you can build a hydrogen bond network, right, between water molecules. And whenever water molecules build a hydrogen bond network, they turn into like hexagons, right? They make like hexagon shapes because of the bond angle, right, of between the two oxygens, right? And so they'll make hexagon shapes, and that's the reason why whenever you look at a snowflake, if you've never looked at a snowflake before under a microscope, they're always six pointed, right? And the reason why snowflakes are always six pointed is because water does this thing called hydrogen bonding, right? Where one of the oxygens is attracted to the hydrogen, right? That's connected to another oxygen. They make this network of like six-sided figures, hexagons, and those will manifest themselves as six-sided or six-pointed snowflakes all the time, right? The other consequence of this too is that since hydrogen bonding occurs and they make these six-sided hexagons, there's a lot of space in between. And so when water freezes into ice, the water actually gets less dense because of the space in between the hexagon, right? And so that space between the hexagon makes it less dense, and when it's less dense, it floats in water, right? Because anything that's less dense than water, which is 1 milliliter per gram, right, will float. And ice floats because when water freezes, it makes these hexagons between the water molecules, and the empty space makes it a lot less dense. Okay. So last thing, right? Which of the following atoms can participate in hydrogen bonding? Is it oxygen, nitrogen, fluorine, or all of the above? And I might not have said it in the video, like I said it a second ago, but I said any electronegative atom, right? And oxygen was the one that I used as an example. But remember, anything that's over in the right-hand corner, upper right-hand corner of the periodic table is electronegative. And so nitrogen is also electronegative, fluorine is also electronegative, and so all three of those can form hydrogen bonds. That actually ends our lecture on chemical bonding. We'll come back on Thursday and talk about chemical reactions, right? And so I'll see you on Thursday. Thank you very much for watching.